zumindest wo wir also letzte Woche geendet haben, war, dass wir möglichst allgemeine Voraussetzungen gesucht haben, auch an Randbedingungen und dergleichen, auch an die Bilinearform, also an den Differentialoperator, um Existenzaussagen machen zu können mit Hilfe von Lex Milgram, also auf theoretischer Basis, von ganz allgemeinen elliptischen Randwertaufgaben zweiter Ordnung. Jetzt möchte ich hier noch kurz eine Erwähnung machen, dass im Falle der Existenzaussagen nur gefordert wird, dass die rechte Seite, das nannten wir immer B, dass das eine stetige Linearform ist und nicht, dass es wie üblich gegeben ist als Linearform Integral f, wobei v dann eben aus unserem Lösungsraum, hier der im Hilbert-Raumfalle das gleiche ist wie der Testraum, liegt. Also f hier ist immer angenommen, die rechte Seite als eine L2-Funktion und das ist im Allgemeinen nicht unbedingt notwendig, um Lex Milgram anzuwenden. Genügt es, dass man hier eine ganz abstrakte Bilinearform hat, wie das zum Beispiel im eindimensionalen Fall möglich ist, wenn man hier die Dirac-Distribution sich anschaut, also eine Punktauswertung an einem Punkt Omega innerhalb dieses Intervalls, dann ist das weiterhin eine H1-Funktion. Also da V eine H1-Funktion ist und im eindimensionalen H1 in den Raum der stetigen Funktionen einbettet, macht dieser Ausdruck also Sinn. Also ist die Punktauswertung, also die Dirac-Distribution im eindimensionalen Fall tatsächlich eine stetige Linearform auf H1. Das kann man so definieren und daher kann man im eindimensionalen Fall auch solche Punktquellen zulassen, also Quellen oder Senken, die tatsächlich nur in einem Punkt entstehen oder dort wirken. Das ist im zweidimensionalen schon nicht mehr der Fall, oder im höherdimensionalen, einfach weil H1 nicht stetig einbettet oder überhaupt einbettet in den Raum der stetigen Funktion. Das werden wir die Woche dann in der Übung sehen, dass das im eindimensionalen, dass diese Einbettung gilt, im zweidimensionalen, dass es hier ein schönes Gegenbeispiel gibt. Gut, so viel nur zu dieser Zusatzbemerkung. Okay, so I switch back again to English. I want to give a short overview about the result we worked out the last week. That's about general assumptions for the solvability of such boundary value problems of second order with the solution space. Here in this sense, our functions have to be in H1, and we have homogeneous Dirichlet boundary conditions on this segment of the boundary gamma 3, such that our conditions of the theorem of Lex Milgram are satisfied, and this theorem ensures us the unique solvability of our boundary value problem. However, these assumptions are that our domain is bounded and is a bounded Lipschitz domain. The coefficients are, with respect to the differential operator, are bounded, and also the divergence with respect to the advective coefficient is bounded. The right-hand side is a L2 function, and well, in the case that we have gamma 1 belongs to the Neumann boundary condition, gamma 2 to the mixed boundary conditions. If we have one of these conditions, we also assume that the normal direction on the boundary of the coefficient corresponding to the advective term also is a bounded function. Furthermore, this is the quite usual assumption. We assume that the coefficient tensor with respect to the highest order derivative of our elliptic equation, of our elliptic differential operator, is uniformly elliptic. That means it satisfies this inequality. And on the boundary, our boundary conditions are L2 functions in all three segments. There are some further assumptions. The next three assumptions are important to assure the ellipticity of our bilinear form, which is a really necessary assumption, condition for to apply the Lex-Milgram theorem. The first means that the coefficient with respect to the reaction term minus 1/2 over the divergence of the coefficient with respect to the advective term has to be greater than 0. In the case of a Neumann boundary condition, we also assume that the normal component of this coefficient is greater than 0. And in the case of a mixed boundary condition, we have this condition. Well, then we have some further quite technical, complicated, but not that strong conditions. They only ensure that there is a little domain or a little segment on the boundary such that all these assumptions are rigorous. That means, for example, there exists a subdomain belonging to our domain omega such that this inequality indeed is not only greater than 0, but greater than a scalar which is indeed greater than 0, and so on. Quite important is the last assumption. That means if we have inhomogeneous Dirichlet boundary condition with the boundary condition is G3, then we assume that our then there has to be a H1 function on the whole domain omega such that the restriction of this W function is on this boundary gamma 3 is nothing but the boundary condition G3. So in these cases, the theory of Lex-Milgram ensures us the unique weak solvability of the boundary value problem. Well, I want to remark briefly the case of fourth-order boundary value problems. For example, we're looking the homogeneous Dirichlet problem for biharmonic equation. That means we're in the classical sense we are looking for 4 times continuously differentiable function u that satisfies these both equations. At the boundary, we have homogeneous Dirichlet boundary, and also the normal component of the derivative vanished as well. And the B Laplacian coincide here with the right-hand side. This operator, Laplacian square, is nothing but we apply the Laplacian operator twice on this function u. Well, in the 1D case, this reduces to only the fourth derivative. That we now have here 2 different boundary conditions for only one function is really necessary to ensure the uniqueness. For example, if we skip this condition of the normal component of the derivative, so we only have this condition of the homogeneous Dirichlet boundary condition, then, for example, of course, on the right-hand side f equals to 0, then, of course, the constant 0 function is a solution. But also, maybe on the circle, in the 2-dimensional case, on the unit ball, also this function is also a solution, satisfying, of course, the first equation. So the B Laplacian applied on this function equals to 0, and due to the choice of this constant and the radius of this unit ball, it indeed has homogeneous Dirichlet boundary condition. So, however, for higher ordered boundary value problems, there's indeed we have indeed to require more boundary conditions. So, of course, this is the formula we already know from the tutorial. That this holds for arbitrary functions in H2, belonging to H2. And if additionally function u indeed belongs to H4, then we can replace the function u here by the Laplacian of u, and we obtain this function, this equation here, that the integral over the product of the Laplacian u times Laplacian v equals to the right-hand side here. The first guy here equals, due to our problem, assuming that the u is the solution of the B-Laplacian, of the B-harmonic equation, this integral equals to the integral of the right-hand side f times v, and due to our boundary conditions, both surface integrals here vanish. So that means that with this solution space, this is the space of all H2 functions, satisfying the boundary conditions, we obtain the following variational formulation. That means that we are looking for a function belonging to even this function space such that it fulfills this equation. Here our bilinear form is, of course, the integral of the product of both the Laplacian of the Laplacians of both functions, and the right-hand side is again the linear form, the integral of the right-hand side times the test function. Okay? So, more general, boundary value conditions of order 2m leads to a variational formulation in Hm, or in if we have Dirichlet boundary conditions in Hm indexed by 0. Okay. So the next quite important and interesting question is about the regularity of the solution. Often we need more regularity, not only for our solution of the elliptic boundary value problems, not only that the solution belongs to H1, but maybe for interpolation of the solution, or in context of error estimates or other interesting topics. We're interested in if is it possible to extend somehow the regularity. That means that the solution do not only belong to H1, but maybe also belong to H2. That means that the weak derivative of the solution U even belongs to H1 and not only more to L2. However, to ensure such a regularity, more regularity on a solution, we of course have to assume more assumptions on our, for example, on the smoothness of our boundary of the domain, but also on the shape of the domain, and of course on the smoothness of the coefficients and of the differential operator, and on the right-hand side also, as well as on the boundary conditions, and on the kind of the transition from one boundary condition to another boundary condition is maybe important as well. However, I just want to state one nice useful result here without any proof. There holds, if we assume a bounded C2 domain, omega, that means that it is there the boundary can be locally described as a graph of not only a Lipschitz continuous function, but a C2 function. And the complete boundary is of the domain now is on the complete boundary of the domain we assume a Dirichlet boundary condition. Furthermore, we assume that the coefficients with respect to the higher ordered derivatives even belong to C1, and further the other coefficients belong to L infinity, so they are bounded, and the right-hand side is still a L2 function. Furthermore, there exists an H2 function such that the restriction of this H2 function W is this boundary condition G3. Then our solution indeed belongs to H2 and can be estimated by the L2 norm of the more or less of the solution U this is the solution with respect to the corresponding homogeneous boundary problem, where we where we shift the boundary condition to on the right-hand side of the equation, plus the L2 norm of the right-hand side, plus this the norm of this W function. Okay, the disadvantage is that due to this assumption that omega has to be a C2 domain, it holds not for polyhedral domains. What we are in particular interested for discretizing and triangulations to do numerics. But nevertheless, we can, it is possible to obtain this result for polyhedral domains with the additional assumption that our domain has to be convex. Okay? And this additional assumption indeed is crucial, since there are some simple examples that of boundary value problems, such that on domains, for example, with reentrant corners, that means if our domain, for example, looks like that, more or less, then there are examples that this regularity assumption does not hold on such a domain. Okay, so now let us start to do some discretization with the finite element method. To exploit our theory we developed now in the previous section, we assume, of course, that our domain omega is a Lipschitz domain, and hence the finite element discretization of the boundary value problem with the corresponding boundary conditions leads to a Galactican approximation for the variational formulation we already have seen in the second section for the Poisson equation, and now we have an arbitrary or a more general bilinear form A, linear form of the right-hand side B. Then this W function corresponds to the non-homogeneous Dirichlet boundary condition, such that restricted on gamma 3, that is this boundary condition. Then the previous section ensures the solvability in the weak sense, but now a disadvantage is that in general our bilinear form is no more symmetric. That means that the variational equation, and then from this point of view also the Galactican approximation, is no more equivalent to the Ritz method, which is based on the minimizing problem. For this, we have to make a choice now, which we want to follow, which ansatz of this both. And we now do this variational equation ansatz in the following. Well, the arbitrary or quite general Galactican approximation is the following. We are looking for a function u belonging to such an ansatz space, which is finite dimensional, such that the bilinear form tested in the first argument, we have our solution UH. The second, the bilinear form, which also belongs to this ansatz function, is equal to such a linear form. Well, in this, by a non-homogeneous Dirichlet boundary condition, here it is all, this linear form somehow works with this non-homogeneous Dirichlet boundary condition. Well, it is desirable that our chosen finite dimensional ansatz space VH is a subset or a subspace of the theoretical space V. V in our case is mostly H1, or H1 indexed with 0 in the case of Dirichlet boundary conditions. And finite element discretization, they satisfy this in inclusion, are called conforming finite element discretization. If this inclusion is not satisfied, then this discretization is called non-conforming. But we restrict now in the conforming discretization methods, and our ansatz space now is defined with respect to triangulation, and we define piecewise the local functions, and in that case, or with the goal that our basis functions of this ansatz space here has a very small support. This leads to a very sparse stiffness matrix and leads to quite good Okay, for example, in two space dimensions, this triangulation consists of triangles, as we already have seen in the second section, and generalization in more space dimensions, for example, leads to this definition. A triangulation of a Lipschitz domain omega consists of a finite number of subsets k of omega with the following properties. K is a closed set, each k of the triangulation, each k, the interior of each k is non-empty and a Lipschitz domain. The union of each k of the triangulations is the closure of the whole domain. And if we have distinct subsets K1 and K2 of this triangulation, then the intersection is empty. That means that the interiors of these subsets are disjoint pairwisely. And, well, these subsets K, the elements of our triangulations, are called oftentimes the elements, and are a decomposition of the closure of our domain omega. They do not overlap. And, well, this is a quite general, abstract definition that still allows, for example, curved, bounded elements, which we are maybe looking later on. So that's why here, for example, we are not yet so specified into simplexes or other specific cases. For example, the property 3 of definition in the second section, where we defined a triangulation, is still missing. That is that, for example, the intersection of two triangles that is not empty is either a vertices, which is a shared vertices. That means that it is a vertices for both triangles, or it is an edge for both triangles. And in our abstract definition here before, it is still missing, but we reformulate it later on for the several types of elements. Well, of course, we define H, again, as usual, as a measure of the size of elements, and mostly it is defined as follows, as the maximum of the diameter of those elements. That means, for example, it is the length of in the case of triangles, it's the length of the largest vertex edge that occurs in the triangulation. Well, furthermore, we are interested in a local ansatz space. That means for each element of the triangulation, we are looking for the function space on such an element. In this case, if we already have given a global ansatz space, then the local ansatz space for a given element of the triangulation is nothing but the restriction. That means that the global Ansatzspace is a subset of arbitrary functions such that the restriction on an element of an arbitrary element again belongs to the local Ansatzspace. Well, as we have seen in the section 2, in the case of linear finite element method with triangles as triangulation, we have chosen at each triangle the local Ansatzspace curly P1 that is nothing but the set of all polynomials of degree 1 on this triangle K, capital K. And in the following definitions, we assume that this local Ansatzspace always consists either on polynomials or on polynomial-like smooth functions, such that, however this is defined in particular, we assume that this function always is a subset of this intersection. So and the local Ansatzspace is a space of continuous functions which are in particularly weak differentiable. Okay. This result is a very nice result, since it shows us that if we assume that our local Ansatzspace satisfies this condition, so it is continuous, each element of this local Ansatzspace is continuous of each element K and is at least once weak differentiable, then we have this equivalence. That means that our global Ansatzspace is a subset of the function space of all continuous functions, if and only if each element of the global Ansatzspace indeed is a H1 function. So this is why we want to ensure that our solutions of the finite element method are continuous functions. And in the case of Dirichlet boundary conditions, we have here respectively pendant. So I also want to give proof for that result. But in the case of that our global Ansatzspace belongs to each element of the global Ansatzspace is a continuous function, we are talking about C0 elements. But for example, as we have seen before, a boundary value problem of fourth order, we do not need only C0 elements, since our since our solution has to be a H2 function, and in the case of a conforming finite element approach, also our global Ansatzspace has to be a subset of H2. That means, there's a generalization of this result before, that means that also our global Ansatzspace has to be not only continuous, but continuously differentiable. Okay, and now we introduce degrees of freedom. Degrees of freedom are a finite number of linear functions. They somehow evaluate our elements of the local Ansatzspace. For example, these linear functionals are nothing but evaluations of the function itself at the nodes, at edges. But they also can be, in this case, if all our degrees of freedom are nothing but evaluations of our function itself at the nodes, then we are talking about Lagrange elements. But of course, there are further possibilities of linear functionals, for example, integrals over the whole element, or the evaluation of a derivative of the function belonging to this local ansatz space in some points, or however. Now we want to concentrate in these Lagrange elements, but in the case that we are looking for C1 elements, derivatives of course are necessary, so Lagrange elements would not be sufficient. Okay, and now the global ansatz space is defined by the specification of the local ansatz space and the degrees of freedom. So we decide the local we determine for a local ansatz space, we decide for a useful degrees of freedom, set of degrees of freedom, and with this we obtain a global ansatz space. Of course, the choice of degrees of freedom and the local ansatz space has to be done in that way that at least we, due to the Satz, okay, it's not the result before, that we ensure that the global ansatz space, all elements of the global ansatz space are continuous, such that we ensure that the elements of this global ansatz space are also in H1. And furthermore, we have to ensure that also our Dirichlet boundary conditions are enforced in the nodes at the boundary somehow. And this leads to compatibility conditions on the triangulation. And as we already have seen in the section 2, due to the choice of degrees of freedom, there is an interpolation problem which has to be uniquely solvable. This is very crucial for our method. Furthermore, not only on such an element K, the interpolation problem has to be uniquely solvable, but also for each phases of the element K. So let this triangle be our element K1, and this triangle, for example, at our element K2. Then the intersection here, this set, this is the face, capital F, belonging to K1 as well as to K2. And also on this face F, the corresponding interpolation problem has to be uniquely solvable, such that indeed we enforce here continuity of the function of the global domain. Okay. And the following finite elements we are defining below are defined on their basic domain, on such a domain K, and defined through a local ansatz space and the set of degrees of freedom. And these we are introducing in the following below, satisfying these mentioned properties. So now we set with this curly P indexed with small k, we denote the set of polynomials of degree k in D space variables. And they look in general as follows. And of course, since these are only polynomials, this is nothing but a vector space, a finite dimensional vector space on each element k. And each element of each polynomial is arbitrary, often differentiable. That means that this local ansatz space is a subspace of all function spaces we have introduced before. For example, H1 or H2 doesn't matter. This space of finite dimensional space of polynomials of degree small k is always a subset of these functional spaces. Furthermore, there holds such a dimensional formula. I think we will verify that in the tutorial next week maybe, or the week after. And now to start, we don't want to start with curved boundaries elements, but much simpler with simplicial finite elements. That means that the basic domain K, these K's, elements are nothing but simplexes. And for this, we define as follows a simplex. A regular d-simplex of so we call a set K a regular d-simplex when there exists a distinct points A1 to a d plus 1 such that they will be called edges, vertices, such that these vectors A2 minus A1, A3 minus A1, and so on, till a d plus 1 minus A1 are linearly independent. Well, this is a quite abstract definition, but that means nothing but, for example, in the two-dimensional case, we have three distinct points, A1, A2, A3. These are the vertices. In such a case that this vector A2 minus A1 and A3 minus A1, these two vectors are independent. Then it's called a regular non-degenerating d-simplex. And d, in our case, or in this two-dimensional case, d, of course, is 2. Maybe I'm able to sketch the case d equals to 3. In this case, we have 4 points somehow. And we have to ensure so this is something like a tetrahedron. Maybe one can see that. In the three-dimensional case, these vectors span this tetrahedron, or even a three-dimensional vector space. However, these three vectors have to be linearly independent. Then this simplex, this tetrahedron, or this triangle in the two-dimensional case are called regular d-simplex. Furthermore, one can describe in this case our simplex as the set of convex combinations of these d plus 1 points. And this is nothing but, well, all convex combinations, such that here these coefficients lambda I sum up to 1, and each coefficient is in between 0 and 1. Furthermore, each phase of this simplex can be described as a d minus 1 simplex, a regular d minus 1 simplex, which can be described or defined by d points from this d plus 1 set of points. That means if we are, for example, interested in this phase, this phase is nothing but a d minus 1, in our case now d a 3. That means this phase is a 2 simplex, and it is spanned by A1, A2, and A4. And again, we have to, not again, but also to ensure that this is a regular 2 simplex, the vectors a2 minus a1 and a4 minus a1 have to be linearly independent. Okay, some examples. In the 2-dimensional case, we have triangles as simplexes. And we have 3 faces. In the 3-dimensional case, we have a tetrahedron and 4 faces. And for example, in the 1-dimensional case, it's quite boring since we only have, two faces. They are nothing but only these boundary points, A1 and A2 itself. Okay. We say simplex is degenerated in cases when this assumption 3.42 is not satisfied. That means, for example, that we can understood such a line segment here as a regular 1 simplex, since this vector, of course, is linearly independent. But also we can understand it as a degenerating 2 simplex by introducing a further point. And then we have a set of 3 points, which is for a 2 simplex assumed here. We need a set of 3 points. But now these vectors a2 minus a1 and a3 minus a1 are linearly dependent, such that now this is either a regular 1 simplex or a degenerating 2 simplex. So now let us introduce barycentric coordinates. We call barycentric coordinates, we call these unique coefficients from this definition here. For each x in our simplex, for example, here is our simplex, here is our point x. We want to describe a convex combination of our vertices point a1, a2, and a3. Then we can describe it by such a convex combination uniquely. And this leads to unique coefficients, lambda 1, lambda 2, and lambda 3. All they are in between 0 and 1. And these coefficients are called barycentric coordinates. So one can describe x, here our point x, by the standard coordinates or even by such barycentric coordinates. Well, but as we see here, we get unique coordinates, barycentric coordinates for each several point x, such that we have a map built from our element k, our triangle in this 2-dimensional case, for example, from our simplex into the set of real numbers. Okay, and now we collect our points a1, a2, and a3, the components of these points in such in the columns of a matrix, and this leads to that the condition of a convex combination, that is nothing but this equation and also this equation, now are combined in this system of linear equations, where the matrix B is defined as follows, as written here. Here are the components of the point A1 written in this column, and so on, and the next column are the components of the point A2 written, and so on. And in the last line, we have in each component 1. This is to ensure that the coefficients sum up to 1. Okay? Well, and now to obtain a formula to compute our lambda, it would be quite useful to know something about regularity or invertibility of this matrix B. And indeed, in the case of a regular simplex, this matrix is regular. That means invertible. So this is due to the fact that the determinant of B is nothing but the determinant. Now we use the linearity of determinants in the columns. It's nothing than, well, the following: a d1, 1, a1 minus a1, 1. So we only subtract in each in the columns the first column from the second column, and so on, and the last column, the first column also from the last column, and obtain the following. And the last column now looks like this is 1d minus a 1, 1, and so on, and a d minus a d1. Okay, this is wrong. Since we subtract 1 from 1, we have here in the last line, we have 0. Okay, plus the sum over all determinants of matrices looking like a11. So we keep the first column, and in the eth column, or the jth column, from j equals to 0 up to d, plus 1. This is the point. D plus 1, yes. D plus 1 and D plus 1. Okay, up to D plus 1. We replace the column of B in the jth column of B by the first column, such that again we have here the same column as we already had in the first, and here we end up d plus 1 minus 8d. This is okay. So we only use the linearity of the columns of the determinants in the columns, and here we did nothing but replacing the column of B, which is nothing but the point Hj, the components of the point Hj, by the components of the point A1. However, since now we have two equal columns, each determinant of this sum within this sum equals to 0. And of course, due to the fact that there is a regular simplex, all these vectors are linearly independent. That was the assumption of a regular simplex. And all these vectors are also, due to the last line here, linearly independent from the first column. However, this is a regular matrix such that the determinant of this matrix does not equal to 0, and therefore also the determinant of B does not equal to 0, and this is why B is invertible. And since it is invertible, now we have a quite nice formula for our barycentric coordinates, lambda I for each point x. This is nothing but, okay, we have to invert somehow the matrix B. and this is called matrix C, and the components of matrix C now here are these coefficients Cij and so on. But we see that this map to get a barycentric coordinate from an arbitrary point x within our simplex is an affine linear map, such that this map of the barycentric coordinate belongs to this local space P1. Okay, now a quite interesting thing is that the level surfaces of this function, that means the set of all the set of all points within our simplex K, such that the ith barycentric coordinate lambda I equals to some scalar mu. This defines an even level surfaces, and this is nothing. And this corresponds with the intersection of the hyperplane. This is sketched here with the simplex K. So this surface, this level surface is nothing but this or this. It depends on your scalar mu line here. Okay. However, if we have two distinct scalars on the right-hand side, so we have two distinct level surfaces for the same barycentric coordinate, these surfaces are parallel, and in particular, the level surface with respect to the scalar mu equals to 0 is nothing but the face of the simplex K we get if we neglect the point A1, which with respect to this component, to this barycentric component. Okay? So if, for example, lambda I is equals to 1, then this is the barycentric, then all other lambda components, all other barycentric components within this simplex has to be 0, since all these points within the simplex are convex combinations, such that the only point which can be described by this barycentric component ith equals to 1 and all other are 0 are, of course, the point AI. And on the other hand, if lambda I equals to 0, then we are here on the other side on this face and describing all these points on this face. Okay? Okay, so that's how barycentric coordinates can be defined for arbitrary x in Rd. Since this formula also holds for arbitrary vectors x. And if we do so, then we have here an equivalence, of course, that our point x belongs to the simplex if and only if all barycentric coordinates are in between 0 and 1. This is nothing but the reformulation of the convex combination of x by the vertices of our simplex. Furthermore, we obtain, due to Cramer's rule, applied on this equation of linear equations, system of linear equations, that for the ith component of the solution of this system of equations, that is lambda I, is nothing but 1 over the determinant of B, that we can apply this Cramer's rule since we know that B is a regular matrix, times the determinant of the mat of this matrix, where only the ith column is replaced by, well, by here the right-hand side in this case. Okay? So furthermore, since now we have a relation from the components of a vector x, or the points in a simplex, and the barycentric coordinates by this matrix B, there holds in general that the volume of our simplex K here is nothing but the volume of a reference simplex, and I will define what a reference simplex is, times the determinant, or the absolute value of the determinant of B. Well, I think in the two-dimensional case, in section 2, for the case of finite element method applied on the Poisson equation, I guess you already have introduced such reference simplices. And in our case, they are defined quite similar. A reference simplex, a capital K hat, is nothing but, well, the simplex which corresponds to the points A hat 1, this is the origin, and A hat I plus 1 is nothing but the unit vector AI. That means it is all components are equal to 0 except the ith component that equals to 1. And that holds for all I equals to 1 up to D. However, in the, for example, the two-dimensional case, I think this is the reference simplex you already know. This is, here is A1 hat. Here, when this is 1, A2 hat. Here we have A3 hat. And then this is capital K hat, so our reference simplex. In the three-dimensional case, I draw it a little bit more flat. So we have here again A1 hat, here again A2 hat, A3 hat, and here maybe A4 hat, such that the simplex now is nothing but this okay? So these are reference simplices. And we can restrict ourselves always to these reference simplices by this formula. Okay, but the volume, now due to this formula and the structure of our matrix B, the volume of this simplex is nothing but 1 over the factorial of D times this absolute value of this determinant of B. And therefore, due to this formula we obtained by Cramer's rule, we get that the ith component of the barycentric coordinate of a point x is nothing but plus or minus, it depends on the arrangement of the coordinates, the volume of this convex combination divided by the volume of our simplex K. So for example, in the two-dimensional case, the volume of K equals to the determinant of B divided by 2, if and only if the 3 points, the 3 vertices of K are arranged counterclockwise. Furthermore, in the two-dimensional case, the barycentric coordinates are nothing but, now we can understood them as due to the formula, as one slide before here, due to this formula, that these barycentric coordinates are nothing but the relative area of the following. I will draw a picture, maybe one can understood it much better. So this is our simplex K. This is our point X. So, and with this, replacing this, the point A3 with this point X, we again obtain a simplex, or at least a set of convex combinations here. And this is nothing but this convex combination. We all just replaced one point, one vertices with X. And the volume of this new simplex divided by the volume of the simplex capital K itself, this is here below. This is nothing, this relation of both volumes, this is nothing but our barycentric coordinate lambda I. In our case, we replaced the third point, so this is lambda 3 of X. Okay? So the relation of both volumes. And this does not only hold in the two-dimensional case. In the two-dimensional case, these are relative areas of the triangulars, but analogously it holds for the three-dimensional case or more dimensions if they wanted. Furthermore, it's quite nice that, rather simple, it is possible to specify geometrical characterizing points. For example, the midpoint. The midpoint of one edge here is nothing but 1/2 A1 plus 1/2 A3 plus 0 times A2, such that for this midpoint, the barycentric coordinates are 1/2, 1/2, 0. Okay? As you can see here. And furthermore, also the barycenter of such a simplex can be given quite easily in the following way. It is nothing but the arithmetic mean somehow of all points. Yeah, so in our case, the barycenter, it looks more or less close to this point X, but the barycenter is nothing but, in this two-dimensional case, but 1/3 A1 plus 1/3 A2 plus 1/3 A3. Okay? And this is the formula for arbitrary dimensions. Well, so let's come to specific finite elements. In the first case, we want to look again to linear finite elements, to an approach with linear finite elements, at least locally with simplexes. with such regular simplexes. So we assume that our simplex capital K is a convex combination of d plus 1 points. And our local Ansatzspace defined on this simplex K is, as we already have seen in the second section, the space of polynomials of degree 1. Furthermore, the set of degrees of freedom are nothing but d plus 1 evaluations at nodes exactly at the vertices of our simplex for such functions, such linear polynomials. Well, then this interpolation problem, which is given on this simplex, that means that we have to find for given d plus 1 scalars a polynomial belonging to this local Ansatzspace. That means in our case a polynomial of degree 1, satisfying that the evaluation of at a vertices ai of such of this function p is nothing but ui. And of course we know due to section 2 already that this problem is uniquely solvable. And okay, this corresponds to the question of somehow of the inverse image of a linear map that maps from this local point, a local Ansatzspace, back to this set of given scalars, the d plus 1 given scalars. And this is the set of degree of freedom. So, but now still the dimension of this vector space is nothing but the number of degree of freedoms, and this is d plus 1. And due to the formula we already have introduced before, we also know that the dimension of this local Ansatzspace is d plus 1 as well. We have a map in between two finite dimension spaces with the same dimension. So that means that the solvability of this interpolation equation is equivalent to the uniqueness of this of a solution of this interpolation problem. So it suffices to give to write explicitly a solution of our interpolation problem, and due to the to the same dimensions we have in this map, we already know that this solution is unique for the interpolation problem. Well, to describe a solution of this interpolation problem, we do the ansatz, the approach of specifying these so-called shape functions. This is in this case nothing but our already known nodal basis. And hence, of course, this is the solution of the interpolation problem we are interested in. Okay, now to describe these shape functions or these nodal spaces in the sense of our barycentric coordinates. In the linear case, it's quite easy to do. since this shape functions, or our nodal base, is nothing else but this barycentric coordinates. Why does this relation hold? Okay. Again, in the two-dimensional case, we have here A1, we have here A2, we have here A3, and the interpolation problem gives the problem that our function u, belonging to the local ansatz space P, has to satisfy that u, ai equals to ui in each three vertices. And now we say that ux is defined as the linear combination of ui nix, where this nix is nothing but the nodal basis. That means that at this point it is ni also belong to this local ansatz space. In our case now it is the set of polynomials with degree 1. So this function is uniquely determined in 3 points. Okay? But again, in the slides before, we have seen that lambda I is also an affine linear function. So also this function is uniquely determined in 3 points. Well, but we have seen in the slides with respect to the certain level surfaces that lambda I equals to 1, well, at the point ai. And lambda I equals to 0, that, for example, lambda 3 equals to 1 here, and lambda 3 equals to 0 in this level surfaces. So lambda 3 is 0 at this level surfaces, and parallel to this, more or less, it equals to 1 at this level surfaces. However, since it is affine linear, determined uniquely in these 3 points, also ni, this is why for this linear ansatz, these barycentric coordinates coincide with our nodal basis. Is 0 for I does not coincide with j. Okay, so and to end up for today, let us come to the quadratic approach with those simplexes. We assume again that our simplex capital K is a convex combination of d plus 1 points, a1 to a d plus 1. But now our local ansatz space does not only consist of the polynomials on this simplex K with degree up to 1, but with degree up to 2. Okay? And we also extend the degree of freedom. That means that we are not only interested in the evaluations of at the vertices, but also at the midpoints, at the edges of the edges. Yeah. So now the degrees of freedom are, in the two-dimensional case, again, not only evaluation of the function at these vertices, but also at these midpoints. Okay? And by this donation, we denote these vertices at A1, A2, A3, and the midpoints as A1, 2, A2, 3, and A3, 1. Okay? So, however, again, in this case, the number of degrees of freedom coincides with the dimension of this local ansatz space. So again, we have it suffices to show that the interpolation problem is solvable to that would also imply the uniqueness of the interpolation problem. Well, how we can verify this formula? Okay, the second equation comes again from this formula. We have seen some slides before. We maybe verify in tutorial next week's. And this first equation, well, that comes from, well, we have to count all these degrees of freedoms, all these numbers of vertices and numbers of midpoints. For example, the next slide has a nice picture. Yeah, there's, of course, we have d plus 1 vertices. Then, starting from one vertex, for example, A1, we have d edges, and for each edge, we have one midpoint. So we have d plus 1 vertices, and from one beginning vertex, we have d midpoints. Now we go to the next vertices, maybe h2, and count all midpoints on edges in between h2 and a point we not yet have counted. So there we have d minus 1 edges in this case. Okay? So, however, successively, iteratively somehow, we do this algorithm more and more. So we have d plus 1 vertices plus d midpoints from one vertices to the other vertices in these edges plus d minus 1 from the next vertices to the other vertices we have not yet counted, and so on. However, we have this sum, okay, and the formula for this sum is nothing but d plus 2 times d plus 1 half. Okay? This is maybe more or less an explanation why this first equation holds. However, more interesting is now how we get shape functions in this case. So we want to have quadratic polynomials, that means polynomials of degree less than 2. And indeed, these both formulas are the shape functions for the Lagrange elements with quadratic polynomials. Okay. For example, to understand the second guy here, I again draw this simplex. We have A1, A2, A3, and the corresponding midpoints. A12, A23, A31. And, well, we have, for example, we are interested in the shape function that corresponds to this midpoint. Yeah? Then this is the level surface of the barycentric coordinate lambda 1 equals to 1/2, since this is because this is the level surface lambda 1 equals to 1, and this is the level surface lambda 1 equals to 0. Okay? And in the same way, let us draw the level surfaces of the barycentric coordinate lambda, lambda 2. This is lambda 2 equals to 1/2. And this is lambda 2 equals to 1. This is not so important, also not this level surface, but this here is very important. This is the level surface lambda 2 equals to 0. Is it still readable somehow? Okay, however, we obtain that the product 4 times lambda 1 times lambda 2 equals to 1 in this midpoint, indeed, since we have here 1/2 and here 1/2. And for all the other midpoints or vertices, either lambda 1 or lambda 2 equals to 0. For example, in this case, in this phase, lambda 2 equals to 0, and on this phase, lambda 1 equals to 0. So there, indeed, we have a shape function such that only in this point, this function equals to 1. On all other points, it equals to 0. And in the same way, we can explain this function. This is the function corresponding to the vertices. So again, A1, A2, A3, and the midpoints are A1, 2, A2, 3, A3, 1. And now we are interested, for example, for the shape function corresponding to these vertices. And where's my picture? Okay. This is the level surface where lambda 1 equals to 1/2. We already have it used here. And we use, again, this level surface where lambda 1 equals to 0. So, and now we see that the function, the shape function lambda 1 times 2 times lambda 1 minus 1 is indeed a shape function with respect to these vertices. Since, well, at this point, lambda 1 equals to 1. So, and then the shape function equals to 1 as well. At these both points, lambda 1, these midpoints, lambda 1 equals to 1/2. In this case, this second factor equals to 0. And, well, of course, at this phase, lambda 1 equals to 0. That's then the first factor is equal to 0 and the shape function as well. Yeah. So you see that with that barycentric coordinates, shape functions, and bases for our local ansatz space can be found quite easily. Okay, so I think we're finished for today.